I've got my tablet now instead of my laptop, so I can start writing in OneNote. So we're going to start talking about finite difference methods. Now, we've seen that the Euler method, it's like taking finite steps in time. All we're going to do now is extend that idea to space. Now, spatial problems are a bit different because they're almost always boundary value problems. So you have, instead of in time where you can kind of go on endlessly, like time's not really bounded, you put a practical upper bound in there, you don't actually care what happens when you get to the upper bound. In space, you often care about a region that looks like this, right? So this is say my X, right? And I've got known stuff happening at X equals 0. I've got known stuff happening at X equals L. They are my boundaries of my domain, and I have boundary conditions there. Inside here, however, I've got a PDE or an ODE for that matter. I could have an ODE, but let's say I've got a PDE. I've got a PDE that governs the behavior in here. What we're going to do is we're going to break up this interval into a number of finite steps. Right? As we did with the Euler method, we just sort of took a step h, or delta t, or whatever convenient notation it is, and that was our grid. So I'm going to break this up into our discrete grid of points along here. We're going to assume that they're all evenly spaced, even though they're certainly not drawn that way. Kind of stretch this end out a bit so it looks a bit better. We're going to call this delta x, this spatial step, right? So instead of having a time step, you got a spatial step. Very simple concept. What we're going to do is we're going to use information at a number of these points to approximate the derivative operator, right? So our task is we want to approximate the PDE operator on this discrete grid. And we do that by replacing the derivatives with some finite step equivalent. So in the notes, I think I'll probably just jump straight to an example because no, I torture everyone through the derivation. Okay. Here, what I'll do is I'll kind of present an example of what we want to do, and then we'll talk our way through the derivation. I don't have time to go through the derivation in the last 7 minutes, so we'll reserve that for our next couple of hours classes. What we want to do is say we've got the heat equation. No, let's say we've got yeah, let's go Laplace's equation. Laplace's equation on a straight line will become an ODE. That's just df dx squareds equals 0, right? With whatever boundary values we specify. f0 equals a, for example, f of l equals b, for example, right? If they both equal 0, then we've actually got no no actual problem, right? We're only ever going to get the trivial solution. Now, you know that you can solve this. You can do the integral. You can figure out something that fits the boundary conditions. Solution's likely to be a solution of a superposition of exponentials. Let's hope that's not singular. In case this is singular, let's go for let's go for this instead. It's not Laplace's equation anymore, but I know this one isn't singular. This will have sinusoidal solutions, right? So you know how to solve this ODE. You've just got to make your eigenvalues work for 0 and L. What we want to do is we want to replace this thing with its discrete equivalent, right? And how we're going to do that is we're going to set a number of points, if you like, a bandwidth for our approximation. We're going to determine, or we're going to think that we want a certain level of accuracy. We might desire certain stability properties, but we don't know what stability means for this type of equation yet. So let's not think about it too much. But what we're going to do is, when we mean set a bandwidth for our approximation, we're going to say pick some point xi, right? So that's this one here, say. That's point xi. And we're going to use information from xi minus 1 and xi plus 1, right? We don't actually have to choose these two. We could just choose one of them. We could choose this one, and this one, right? It doesn't actually matter. That's our choice, right? The most instructive or sort of classic method chooses these two, right? That's called the centered second order finite difference. Xi minus 1. Right, so we're going to be looking on this set of 3 points to approximate our solution over this region. All right, it's nearly 3 o'clock, so I'll stop there. I'll launch into the derivation of the second order centered finite difference method when we come back at 1600. Does anyone have any questions about this? If you're all happy, just click your happy faces. We should get to the point of being able to implement this idea. We'll see how to program this up, hopefully today or maybe tomorrow if we don't quite get enough time. All right. Anyone got any questions? All right, if everyone's happy and there's no questions, we'll resume at 1600.